Welcome back, everyone. Hope you enjoyed the first session and the quick break. We're very sorry for the hiccups we had with the YouTube streams at the start of the conference. It's our first full online conference, so you guys know that we are not that experienced in this area. But we hope everything is fine now and everything will be good to go for the remainder of the conference. For everyone that was not able to see the intro from the previous session, my name is Daniel Pando, and I'll be hosting the first few sessions here at Al Medina. And I'd like to start with thanking everyone attending, thanking our speakers and our sponsors as well. And here I'd like to leave a special thank you to Aljoscha Krettek. Ilbeam is the co-founder of Ververica and is going to present a session on the long road towards unified APIs in Apache Flink. So if you're ready, Aljoscha, without further ado, I'll leave the stage to you.
Well, thank you for the introduction and thank you for letting me speak here. So I took out the long from the title because the road is not that long, but it's still interesting. So let's dive right in. There's 4 things that I want to tell you about today. The first thing is, what is Apache Flink? Because that's what you need to know to understand the other 3 points. Then we will talk about why there are different APIs in Apache Flink. And then this leads us naturally to the third question, why do we want to unify these APIs? And what does it mean to have unified APIs? And the 4th point is describing the road. How will we actually get there? And the interesting bit here is that the first part is actually the longest part of the presentation, because once you understand what Apache Flink is and what it does and what the APIs do, then the other 3 parts, or let's say the middle 2 parts, they follow somewhat naturally from that. So before we go into this, I want to quickly talk about Ververica. So Ververica is a company that employs the original creators of Apache Flink, and we do develop an enterprise stream processing platform that makes it easy for companies to use Apache Flink. And somewhat recently, the company was acquired by Alibaba. So before that, it was known as Data Artisans. Now the company is called Ververica, and we're now a subsidiary of the Alibaba Group. Some background information about me. So that's a picture of me 5 years ago, I think, wearing the same T-shirt. It still looks roughly the same. So in 2008, I started studying computer science. Then in 2009, 2010, this is some interesting background information. The first papers on Stratosphere were published. So Stratosphere is the research system, open source system, on which then became Apache Flink later. I started working in the group at the university that developed the Stratosphere project around 2012, and there I also met the founders of the Ververica company, or back then Data Artisans. In 2014, Stratosphere was renamed to Apache Flink, and it moved to the Apache Software Foundation to allow us to develop Apache Flink fully into open source. Ververica does not own Apache Flink; it's owned by the Apache Foundation, and we are open source contributors to the project. In 2014, Java 8 was released with support for streams and lambdas. You will see in a bit why this is important, because the APIs look somewhat similar or familiar. Also in 2014, we founded Data Artisans with the goal of developing Flink in the open source. You can also see that's my Twitter handle, that's my Apache email, my Ververica email, and my website, which is just pointing at my GitHub profile, basically. So with that out of the way, we can look at what is Apache Flink. We're going to unpack this in several steps. So the first, let me say that Apache Flink is a distributed data parallel processing framework. And let's see what that means. Sequential computation as opposed to data parallel computation, is when you compute a result in sequence. So say you have a sequence of numbers and you want to compute the sum of them, you can sum up the numbers one by one. So you do 1 plus 2, then you do plus 3, then plus 4, and at the end you would get a result which is 45, if I didn't make a mistake here. So that's sequential computation. Data parallel computation, on the other hand, is a programming model or a paradigm where you split up individual packets of work and you compute results independently, and then you combine those results together. So for example, for computing the sum of numbers, you could first sum up the first 3 numbers, then the next 3, and so on, and then sum up these numbers. In this example, it's obviously not a lot of use to split up this computation, but if those individual computation steps are very processing intensive, for example, if you want to apply a machine learning model on some individual data or compute an aggregation result over some very large data set, that's where the power of this data parallel computation model comes in, where you can where you specify a computation that you can then run in parallel on many different data items, possibly on multiple machines, for example. And that's why I initially mentioned this Java 8 Streams API. The Java 8 Streams API is actually an API that allows you to express data parallel computations in Java. So here in this example, we create a list of strings that has some JSON data in it, in those strings. Then we create a stream from that list, and we say that the stream or that computations on that stream should be computed in parallel. And I think here it depends on the backend, but for Java, for example, it can use multiple threads in parallel to compute these results. And then we specify the different computation steps on this stream. So here we say we first want to apply a map operation, where a map is just saying, given some input, produce some output, and this transforms each element of the stream, possibly in parallel here. And here what we do is we parse the JSON string into a POJO object that has fields and method that allow us to work with that data. Then we apply a filter operation, which would only let through those records or those data items where the age is above 18, and then we apply the count collection on it, and then we get a result which tells us which people in this JSON data were over 18. So that's already a more useful computation that you can express with this data parallel computation model. And the Flink API actually looks very similar to the Java 8 Streams API. But the thing is that this API was developed and released before the Java 8 Streams API was released. It's just some interesting historical tidbit. So with the Flink DataStream API, what you can do is express data parallel computations, just like you can with the Java 8 Streams API. And here, what we are doing is we are saying we want to read a text file. Then we want to apply a map operation on it. That's the same operation that we use in the Java 8 Streams API. Then we want to filter it. Then comes an operation that is specific to Flink here. We say we want to partition that data by a region, because partitioning data allows Flink to send these computations or execute these computations on different distributed machines. We'll get to that in a second. The next operation we say is we want to apply a window operation on this stream. So what we're saying here is, instead of computing a result, for example, these counts for all the data, so from beginning to end, we want to split our stream into windows of 1 hour so that we get these results, these counts for each individual window. So for example, then we could say at 12 o'clock in this stream of data that we're reading from this file, there were so and so many people above the age of 18. And then what we do is, in our previous example, we specified the count operation. What we're doing here is we use, in Flink, it's called aggregate. and we can give it an object that describes how we want to aggregate that data. And what this does is counts these individual people by region, because before we said we partition our data by the region using this key by. And then as the result, or as the final step, we want to write that result out to some file again. Because using the Flink APIs, you wouldn't get the results back as a Java object, but you want to write them out. You want to read that from a file and write that to a file. And the reason why this is so is basically the next step. So once you have, or in Flink, in the APIs, you specify your computation using these APIs. And what these API calls do, or what the code does, is doesn't actually compute a result, but what it does is it builds up a graph of these operations. So for our example, we would have a source, then we would have a filter, then we would have this aggregation, and then we would have a sink. And Flink understands this graph. And what Flink then does, what is the power of Flink, is it can take this graph and split the computation among different execution nodes. So with Flink, so all these boxes here, they would be different machines. For example, in some clouds, or AWS, or in Google Cloud. And what you typically have is you have a Flink master. This is the process that knows the whole graph of the computation that you want to do. And this orchestrates the other machines, which are called Flink task managers, to do this computation. And these Flink task managers, they might have different subparts of this graph, or they might have the same graph. So for example, if one part of the computation, for example, if the JSON parsing is very heavy, then these task managers, they would potentially have more instances of this JSON parsing task than of the other instances. And what Flink does is take care of serializing the data between the different computation steps, sending the data between those steps, and making sure that the overall computation works according to the data flow graph that was created from the specification of the program in the API or in the SDK. So that's what Flink does. It's a distributed data parallel processing system. Let me add some more adjectives to that. So Flink is also fault tolerant, and it is stateful, and it is a stream processing system. So what does that mean? In this computation, or in this graph that we specified earlier, some of the operations are actually stateful operations. So this one we call stateful because the counter in there that counts these different users per region and in these time windows, it needs to keep track of, basically the count is the state. So it would, for example, process one user and it updates the count +1. Then the next user record is processed, it updates the count to 2, and so on. So that's what is a stateful computation. And these other parts of the computation are actually also stateful. So when reading a text file, we have to keep track of the reading position in the file. That is also a state in that computation. And when writing, we need to also keep track of what we have written so far. And there's some of these other operations. So for example, the map is not a stateful operation because the map just gets some input and it produces some output, but it does not affect any state that it keeps internally that it has to update. Same goes for the filter. The filter is an easy operation. It just passes some data through or doesn't pass it through. And when we say Flink is a stream processing system, what this means, or it's a way of looking at things. So the way we look at all data is that all data is a stream. It's a stream of input. Same way you would, for example, if you use the Java 8 Streams API, you might have a finite list of strings, but you still convert that to a stream and treat it as a stream of data. And there's different systems that you can use, for example, to store streaming data. So there's, for example, RabbitMQ, or there's Kafka, which are really systems that are meant to store streams of data where data is coming in real time and it's stored for a short period. And then other systems process that data. And then it sometimes some part you drop it. But there's other systems, for example, S3, or in general, these file system like object stores, they store files. Same goes, for example, for the local hard disk also stores files, but you can think of those individual files also representing a stream of data. So in Flink, we model everything as a stream, and Flink is a stream processing system. And the other attributes I put there is that it is stateful and that it is fault tolerant. So there's some parts that I left out in the previous picture. So for these stateful operations, for example, the aggregation or reading the file or writing the file, Flink has to keep track of that state. And there's some other state, for example, the Flink master has to keep track of which operation is processing which data, or which of these worker nodes, these task managers, is connected to which other nodes to send the data there. And the difficult thing in a system such as Flink, which is distributed and which has state, is that you must be able to deal with failures. So there might be failures in the program if there's exceptions thrown, if there's some bad data. But the more likely thing is that these machines will just fail. There might be network disconnects, the machines might break, or the processes might fail because of garbage collection, out of memory issues. And the thing that Flink as a distributed fault-tolerant stateful processing system provides is that it is resilient to these failures. So it makes sure that if something fails in the computation, it has some backup of that state, we call it a checkpoint, so that it can restore the computation, for example, on some other machine, and continue processing, and can still generate results that look as if the failure didn't happen. That's typically what we call fault tolerance or high availability in these systems. Of course, Flink is more than just an SDK or a set of APIs, but that's a big part of it. So it is the SDKs, but then a big part is also the distributed fault-tolerant runtime, which can take these computations expressed using the API, which are converted to these data flow graphs, and which can execute them on multiple machines. And another important part is the connectors to external systems. If you just had a system that sits there and cannot interface with the outside world, that would be pretty useless. So we have to be able to read from files. We have to be able to read from message queues, such as Kafka, RabbitMQ. We have to be able to write to key value stores, such as Elasticsearch or Cassandra, or Hive, which is from the Hadoop world. So that's a third important thing. And this is often ignored in a way in what Flink is, but it is an open source project that is developed in the open. The communication happens via mailing list. There's an open issue tracker. There is a mailing list for developers where they coordinate development. There's a mailing list for users of the system where they also ask questions and where they help each other. And I think this is a very important part of Apache Flink, is actually this community and this open development. And this is the open processes. They are shaped, if you will, by the Apache Foundation. There's multiple projects in this space, such as Apache Spark, and Kafka that I mentioned is also an Apache project. So that's really setting the processes for how this open source development should work. Let's look at some example use cases. So if you, for example, want to process your shopping list, or maybe your list of movies that you have seen, then expressing them as a data parallel program and using Flink might be a bit overkill for it. And in those cases, it would be quicker if you just wrote a quick Java or Rust program to process that data. But Flink really is useful when you have very large amounts of data that come in real time. So let's say millions of data events per second that come in and that you need to process on, say, hundreds of machines. And for example, Alibaba is building real-time search and recommendation models based on events that they see coming in. Netflix is building session profiles of users so that they can improve the recommendations that they give to users. Banks are using this to do real-time settlements, so where they have the different trade positions in the front of house, back of house, and they need to have a complete view of basically the balance sheet, where they have buy transactions, sell transactions, and so on, and they want to unify that. Advertising companies are using this to do revenue accounting of views on the ads that you see in the browser. And some of the more interesting use cases, I think, are, for example, ING Bank, which train in real-time machine learning models on the data that's coming in real time, and then they do fraud detection on that. So the funny thing here is, what I find funny is the magic carpet fraud, where if you use your card in, say, New York, and then an hour later you use it in Berlin, that's pretty much impossible unless you have a magic carpet to fly there. So that's something that they can detect with this. And there's many companies that use Flink to ingest data, to massage it, to cleanse it, and then put it, for example, to read it from some real-time stream and then put it in a storage system such as HFS or Elasticsearch to make it readable, processable. And just to give you an idea of the scale of what you can do with Flink, these are some numbers from the Singles Day. So this is, it's somewhat similar to Black Friday in the US, where there's this big day in China where there's a lot of discounts and people just go crazy shopping. And here, the throughput of the data that was processed with Flink is 2.5 billion events per second, spread across, of course, multiple different data pipelines, multiple different clusters. But the size of the state that was kept in these Flink operations in total was 100 terabyte. And the number of containers that were used to do this processing was 2 million. So this is just, I mean, I couldn't process this on my on my laptop, but 2 million is just, even I have to, yeah, it's hard to believe for me even this scale, but that's the numbers that we have from the Singles Day. So now you know, hopefully, what Flink is. Now we should try and answer the second question, which is, why are there different APIs? So right now I only showed you the DataStream API. And let's see why there's other APIs. One of the reasons why there are different APIs is that a stream is not always a stream. There is, or you can think of them as, let's say there's unbounded streams, which are just, you receive data in real time and there's always more data coming in, but you can also chop that stream up into parts, then they would become bounded. So for example, one single file on a file system is one part out of a bigger stream of data, and that would be a bounded stream, a single file. So that's the main thing. There's unbounded streams and there's bounded streams. And when you do computations on them, there's some optimizations that you can do which lead to different API choices and different system choices. And we will just look at them now. If you know that you have only bounded data, then you can do something that is called batch processing, where you know upfront you have your data, you can process it, you produce some result, and then you're done. That's it. So the data is complete when you launch your program. On the other hand, if you have continuous streams of data that you want to process, say you have banking transactions that just keep coming in, or you have user events that are triggered by people watching stuff on Netflix, then that data is never done. It's an unbounded stream. And in this case, there are some trade-offs that you need to consider. Say, for example, as I showed earlier, you have some aggregation that counts certain events happening within given time windows, say 1 hour. The problem now is, when do I know when I have seen all data for that 1 hour? Because there might be delays in how the data is shipped to your processing system. There might be network outages, or there might be inherent latency in the system, so that just data always arrives 5 minutes late because it has to go through some other processing layers. And there the trade-off becomes, do I produce results early in continuous stream processing, which means I get results quickly that are potentially not correct, or do I wait for quite a bit until I produce results? And there's two ends of this spectrum. So on the one side, you can produce a new result of your computation for every record that comes in. For example, whenever you see some event, you update your internal state and you emit a new result. So say count was 3, new event comes in, update count to 4, emit that result downstream. This means that you have always up-to-date results. However, what it also means is that you produce a lot more results than potentially necessary. What you can do on the other hand of this, on the other side of the spectrum, is that you just collect all your data, let it sit there, and then say after 1 year you process a result from the data. With this, you would be pretty sure that there's no late data that you need to process where you need to update the count because the previous count was wrong. However, you get your results very late. And there's effects that happen. So for example, if you always produce up-to-date data, you produce a lot more noise. You write more data to the output. So you would, for example, write to your key value store, you would write for every update, you would write to it. So if there's 10 updates and you update the count 10 times, you would also write 10 times. But in the case where you just produce your result after 1 year, you would only produce one update to the outside system. And these outside systems or these other systems in your data processing landscape, they must be able to deal with this difference, that you either produce, say, incremental results or results that updates over time until they settle down to some result, or that you produce one result. So that's the difference in semantics, or how you produce results. And there's also a difference in how you can compute these results. So if you do batch processing, where you have, where you know all the data that you have before, and there will not be no new data coming in, you can use different algorithms or different data structures from what you would use for stream processing. So for batch processing, for example, to compute these aggregates for these different, say, 1 hour time windows, what you can do is you just sort your data by the timestamp, say, and then you do one pass over the data, update, keep a counter for a given window. Then when the time has passed that window, you emit a result, and you continue sweeping through the data. That can be very efficient. However, on the other hand, if you do continuous stream processing, it might be that you receive, for example, a record that should go into one time window, then you receive a record that goes into another time window, then you want to emit results for that time window, but still keep them for later in case some more updates come in for that window and you want to emit more results for that window. So what you need to do is you basically need to keep a point lookup data structure, something like a hash map, where you update the results for a given region, say, or for a given window, and you keep that data there until you decide that you want to drop it. And here the tricky part is, how long do you keep that data? How long do you wait for late data that might update your results? When do you emit the final result? When do you drop it from the data structure? Is the data structure well suited for this kind of access pattern? So there's these different considerations that go into batch processing versus stream processing on the other hand. And that's, in a nutshell, or if you look at it simply, that's the reason why there are different APIs in Flink for stream processing and for batch processing. So what I showed you before is, on the left is this DataStream program, and the DataSet API, which is the API in Flink for these batch use cases where you have bounded data. So the API looks pretty similar. The difference is you have a data set on the one side, data stream on the other side. But the crucial difference is that the DataStream API provides tuning knobs or little points where you can control this trade-off between latency and completeness, and where you can control, for example, I want to have time windows for my aggregation of 1 hour. And the way you do this in the DataStream API is there is this thing called triggers, which specify when we want to produce output. So in this example, we have, say, a speculative trigger which says, even when I'm not sure that I have seen all the data from my window, emit some preliminary results beforehand, but maybe not for every record, but let's say every 5 records, because we don't want to hammer the downstream system that much. And the trigger also says for how long to keep the data after we emitted a first final result, and then how or when we want to delete that data finally from this point lookup data structure. It's basically garbage collection, but on a different level, if you will. There's some other differences, or let's say the difference are in the semantics, is that the DataSet API produces a result once for an aggregation, and as I said, in the DataStream API, you have triggers to control when results are produced. And there's some operations that are more easy to do on bounded data, such as iterative programs where you basically have a loop in the graph. This is, for example, useful for computing machine learning models or PageRank, for example, where you have to repeatedly work on some data. This is hard to express in the DataStream API, where data is just coming in real time all the time and flying all over the place. So that's basically the reason why there's different APIs, in a nutshell. It's also interesting, I think, to look at how these different APIs evolved and how they came to be. So arguably what started this big data processing, distributed processing space was the MapReduce paper from Google in 2004, which is a batch processing system, though there's no stream processing. You have all your data beforehand, you can compute the result, and that's it. There's no continuous processing. There's an open source implementation of this called Apache Hadoop, it's the ideas from the paper taken and developed in Apache as an open source system. Then an interesting system is Apache Storm, which is a stream processing system. So this only does continuous processing, so only has an API for continuous processing, no batch processing. Then there's Apache Kafka, which is a log system. So that's a system that can store data for processing by a downstream system. So you would have your events come in from different sources, you put them in the message log in Kafka, in a message queue, and then a system such as Flink can read from that queue in real time and process data. And the queue is basically a buffer between outside producers of data and between a system that processes this queue. And it allows, for example, to have multiple consumers for the data stored in that queue. Then, by the way, these dates I'm giving are when there was the first usable release of these systems. So for Flink, a first release that only had a batch processing API was in 2011. And for Apache Spark, which is another system in that batch and stream processing, distributed processing space, there was the first usable release in 2012. Then there's quite a gap between, for example, for Flink, there's a gap between 2011 and 2014 when we introduced an API for stream processing. And for Spark, there was a paper about discretized streams and DStreams, which came out in 2013, which is their work for distributed stream processing. And the most recent thing in that space is the Kafka Streams API, which is also an API or a system for doing stream processing when reading from Kafka message logs. This is purely a stream processing system. So you can look at this and then you see that part of why there are different APIs is just that people had different ideas or different use cases and different needs. And initially people only did batch processing. No one thought really about stream processing except in research papers and such. So that's why you have these different APIs, basically. And and in a way, with the power of hindsight, if you could go back in time now to those places, you would maybe design an API or have an API that wouldn't need a differentiation between batch processing and stream processing. You would have a unified API that just allows you to do both. And this is what we are trying to do now, basically, with the efforts to unify the APIs for Apache Flink. The problem with having two APIs is that basically there is two of everything. So if users want to use Apache Flink, they have to see, do I want to do batch processing? Do I want to do stream processing? Maybe do I want to do both? Then you have to learn these two different APIs. So you saw them, they look quite similar, but there's subtle differences in the operations that they support and in the semantics that they support. And it's not easily possible to mix batch and stream processing. So you can't have, for example, one part of your computation be a batch processing thing that produces or processes some data that is just sitting there, and then have another part of the data flow graph, if you will, that does real-time stream processing. Another thing, I mentioned there's these connectors for connecting to outside systems, and the APIs for these connectors and the supported connectors between these systems are different for the two APIs. So there's batch connectors, which can reach from more batchy systems, and there's stream connectors, for example, for Kafka or for PubSub, which connect to more streamy systems. And so if you choose one API, it might mean that you can't use connectors written for the other API and vice versa. And of course, this is more a problem for me as a developer of Flink, but if there is two APIs, it means also that there's code duplication, and we maintain two of everything. Again, there's two APIs, there's two connector APIs, there's two sets of connectors, some of them overlapping. So there's a connector for reading files for the stream API and a connector for reading files from the batch API. So that's quite some overhead for us. And basically, now that you have all this information, now that you know what Apache Flink is, you roughly know what the difference between those APIs is. You really think in hindsight, we don't actually need two different APIs. And that's why our goal is that we want to have one API that can do batch processing and stream processing. And this is not easy. There's some subtle details that you need to figure out, but that is simply said, that's the overarching goal that we want to do. Only one API for both. And if we had this, you would be able to just write your program using this unified API. You don't have to worry about, do I want to do batch processing? Do I want to do stream processing? What if I change my mind later on? And simply put, the idea is that if you write your program using unified API, and if you have unbounded input, the system recognizes this and does more streamy execution with the trade-off between latency and completeness and so on. If you only have bounded streams as input, so you can do these batch optimizations where you, for example, sort the data, then compute the result in one pass, then you get this batchy execution. And this is useful, for example, when you say you have some pipeline where you're ingesting data in real time, and this is working nicely, and you wrote it using the DataStream API, but now you realize you have some older data sitting in files in a distributed file system, and you also want to compute some results from those. If the API is unified, you can just take your program, switch out the sources, and then let it run on that old data. And another important use case that actually quite some people in the Flink community would find quite helpful, and which they talked about at conferences, for example, is that they want to do bootstrapping of a streaming pipeline. So you have some historical data, for example, user interactions sitting in files, and you want to read that in your computation. And then once you have read all that, which fills up some state in your computation, for example, these counters on the windows, then you want to switch over to the real-time source, which is the streaming part of the program. And the system should just deal with this and do the clever thing for batch execution and then do the clever thing for stream execution. So now we get to the last part. How will we actually get there? And this is again often overlooked in developing these systems, but there is actually a process for how such things happen in the community. So what we need to do first is we need to write and publish a flip. This is a Flink improvement proposal. This is a design document that people can propose to the community of developers of the Flink project, which will then be discussed by the developers of the Flink project and the community, the users. There's time for everyone to look at it and see how it will impact the use cases, or if they like it, if they don't like it, if they have other suggestions. Then there will be a vote on the flip, which decides if we accept it or not. And then once that is done, we can start implementing the design and then changing the code in Apache Flink. And I think this is quite an interesting process, and it also forces us, even though we are the original creators of Apache Flink at Verica, we still follow this process and work with the community and are open about what we are trying to do. A quick outline of what we're trying to do is, in my head, it's split into two phases. So what we want to do first is that we want to change, or the rough plan is that the DataStream API becomes the unified API and the DataSet API will be deprecated. And then for this to happen, we need to change the execution semantics of the DataStream API to be useful for batch processing. So if you have a batch processing use case or batch source, a bounded source, then these latency and completeness tuning knobs that you saw in the API, they can just be ignored because they are only there for controlling if you want to emit preliminary results or late results. And if you use the DataStream API and have a bounded source, then Flink should use those efficient data structures and algorithms that it currently uses for the DataSet API to get this more efficient computation. And once we have that, phase 2 would be that we allow mixing bounded and unbounded parts, and they play nicely together so that you can use the efficient data structures and execution style for a bounded part, and then for the streaming part, you use the data structures that are useful for a streaming part. And there's not many more technical details that I can talk about now, but as I said earlier, the important part is understanding what is Apache Flink, understanding the history and the differences, and then it seems very simple and easy, and in hindsight, obvious that this is something that you should do in your APIs. And that's what we're trying to fix now. Again, the devil is in the details, so it's easy to say DataStream API supersedes DataSet, done. But the tricky parts are what are the semantics of these operations. And here, some operations are easy. So there's map, filter, flat map, which are these element at the time operations. We just get some input, produce some output. They have no state. They don't need to keep track of anything. These are very easy to support. I mean, they're basically the same between bounded processing and unbounded processing. What is complicated are the sources and the sinks, where we need to see if we emit differential updates to an outside system, or if we always emit a new result, for example, which plays together with the semantics of the aggregation operations, the windows, and for example, joins, like SQL joins. Here we need to carefully look at the semantics, for stream processing and also for bounded processing, and which makes sense for each of them. So for these aggregations, we need to see, do we only emit a final result after we've seen all the data for batch processing? How do we control it for stream processing using these triggers, and how does it play nicely together? So that's what we need to do. We need to carefully look at the existing operations, the semantics, and find something that makes sense both for bounded processing and unbounded processing. That's basically it for the main part. Now, there's some related bits and pieces that I want to quickly mention, and then we're done. There's one thing that I didn't mention is that Flink already has a unified API. So there's not just 2 APIs currently, there's 3 APIs. and some other APIs, but there is a unified relational API. We call it the table API, which allows you to write relational programs. And actually, you can also use SQL in there. So you can use SQL, or you define your sources and your sinks, and then you can write a SQL program that uses a source like a table, and it writes, for example, an insert into to a table. And this SQL is the same for bounded processing and unbounded processing. And Flink under the hood already does the clever thing of seeing, all the data is bounded. I can do this efficient batch style bounded execution and emit a result only once. Or if the input table is an unbounded table, so you have a stream of data coming in real time, Flink will still take the same SQL program, but execute it differently to have these streaming semantics. So that's something we already have, but this is more for relational and analytic use cases and not for general data parallel processing pipelines like the DataStream API or the DataSet API would be able to provide. And the last thing I want to mention is that there's this project called Apache Beam, which is a project originally from Google, which also aims to provide a unified API, both across bounded and unbounded processing. So they also have these tuning knobs for controlling latency and completeness trade-off, but also across different systems. So this is an API that you can use to write a program and then execute it on Google Dataflow, which is provided by Google, or you can execute it using Spark underneath, or Hadoop underneath, or Flink underneath. And some of the thinking about the semantics of batch and stream processing and windowing and triggers for controlling latency and completeness comes from the Apache Beam project, comes from papers written by people associated with the project, or by articles written by people associated with that project. That's why I wanted to mention it here, because it informed some of my understanding of bounded and unbounded processing and these trade-offs. So it's an important project in that space, I think. So I hope you learned something about these 4 things that I wanted to talk about. What is Apache Flink? It's a distributed fault-tolerant stream processing system. And an important part of it is that it has an active community of users and of developers which develop this in the open source. Why are there different APIs? I think it's mostly for historic reasons, because people didn't think far enough and there were different use cases. Back then, when these APIs were first developed, people didn't think about stream processing using these APIs, and that influenced how these APIs were developed and what they support. There were different execution semantics. This one is, in my mind, quite easy. If you have one less API, that's one less thing to worry about. It's less, users need to learn less. If they want to do batch and stream processing, they only need to learn one API. And for Flink developers, such as me, it's easier to develop if you only have one API to maintain. And the last bit, how will we get there? By carefully looking at the existing APIs, what are the semantics, what works and what doesn't, and then working with the community of users and developers to come up with a plan to unify these API semantics under the DataStream API and eventually get rid of the DataSet API. So thank you, first of all, for listening to this. If you are interested and want to try out Flink or help with it, you can go to the website. You can join the mailing list and discuss. You can join a meetup, for example. This is my Apache email. So this is me with my Apache hat on. And if you're interested in the company, that's my company email, my Twitter handle. And we are also hiring, although it is a bit complicated at this point, I mean, because of the coronavirus situation. But in general, we are hiring if there's interesting people. So if you find any of this stuff I talked about, like thinking about the semantics and the APIs and the SDKs interesting, you can check out our careers page. And there's a position especially for the Apache Flink SDK team, which is my team, where we work on these API SDK related problems in the open source. Thank you. Again, that's it.
Thank you very much, Aljoscha, for the great talk. We are a bit over time, but I'll try to relay the questions that we have here from the guys. So we have a couple of questions from Francisco Sejudo, and he's asking, can you tell a little bit on how to manage the save points and checkpoints to recover from an issue? And if it's possible to have a block pre-assure somehow not to try to swallow all in once at the beginning, if that's strategy is selected, for example, from a Kafka stream topic. And also, is there any mechanism on any way to assert that a task manager gets a job manager if this is down and another job manager pops up?
Ooh, that is a long question. I don't.
Okay, so the first part, can you tell me a bit on how to manage the save points and checkpoints to recover from an issue? And if it's possible for a block to reassure somehow not to try to swallow all in once from the beginning.
What is that? A block or what? Sorry, I didn't hear that well.
This came after the distributed stateful stream processing slides.
So yeah, I mean, I cannot answer some parts of the question, but I think for more in-depth, maybe shoot me an email and then we can try and figure it out. But what he is referring to is that Flink has this feature called save points, which you can use to periodically snapshot the whole state of a computation to some file system. And then you can recover from that snapshot or from that save point in case of a failure. Also, if you, for example, want to update Flink, or if you want to update your processing pipeline, you could take a save point, shut down the whole cluster, then change the program, and then restart it from that save point. Okay. So that's in general what that feature is. But to figure out the specifics of the question, I think it would be better if they send me an email and we talk about it.
That's perfect. Aljoscha, thank you for being available for that. And one very last question from Vinod. Does Flink store some processed state into persistent state for continuing you later, or is everything on RAM and synchronous?
That's a very good question, which connects to that earlier thing I mentioned about checkpoints. So Flink, it's a mixture. Flink has this concept of state backends, which are it's the data structure that is used for storing the real data on which we are computing. And there's a state backend, for example, that stores data in Java hash maps. But there's also a state backend that stores it in RocksDB, meaning it can go to disk on that computation node. But this is just the live state that we're keeping. And what Flink periodically does is it checkpoints the whole state of the computation to a distributed file system, such as Google Cloud Storage or S3 or HDFS, in case there's a failure. So if one of the task managers goes down, Flink would detect that, and then it can restart the whole computation from this data it wrote to the checkpoints earlier. And an important thing is you want to be clever about writing those checkpoints. So you don't want to write the whole state every time you do checkpoints. So if you do checkpoints every 5 minutes because you don't want to lose too much data, what Flink can do is write only incremental snapshots. So it would only write the new data and not write all the data every time we have to do a checkpoint. So that's basically, it's a mix. Flink keeps it potentially in memory, but it snapshots it to some distributed file system for fault tolerance.
Okay. I hope you guys got the answers to your questions. We are a bit over time. Thank you so much, Aljoscha, for the great talk. Hope to see you back again in 2021. Hopefully back to Coimbra.
I would like to see that. Yes, the city.
That's fine. We hope we can see it. You can see it on 2021. So thanks all. Enjoy the quick break. We'll be back in 5 to 10 minutes with Devlin from Microsoft, and we'll see each other soon. Bye.
Have a good day.